You know, from the anti-lock brakes in your car to the smart coffee maker on your counter, intelligent machines are literally everywhere. But have you ever stopped to think about how they actually work? Today, we're pulling back the curtain to reveal the engineering magic that brings all these smart machines to life. Take a close look at pretty much any modern device. You're not just seeing gears and levers anymore, are you? No, you're seeing this deep, powerful combination of moving parts, electronic circuits, and the software that tells them what to do. This whole engineering philosophy, it's got a name: Mechatronics.
All right, so to really get how these systems are built, we're going to follow the entire design journey. We'll start with the big idea, then we'll get into the key components: the brain, muscles, and senses. After that, we'll see how it's all connected with a nervous system, and then, finally, we'll flip the switch and bring our creation to life.
So let's get right into it. What exactly is this integrated design philosophy? Let's break down this core concept.
Okay, this diagram shows the three pillars perfectly. On one side, you've got mechanics. That's all the physical parts that move. Then you have electronics, the sensors and circuits that control everything. And the glue holding it all together? That's information technology, the software, the intelligence. Mechatronics isn't just one of these things. It's the powerful fusion of all three, creating systems that are way more capable than just the sum of their parts.
And this is a really critical point. Mechatronics isn't just a buzzword, and it's not just about bolting a computer onto a machine. It's a complete revolution in how we design things. See, instead of having separate teams working in their own little bubbles, Mechatronics forces them to collaborate from day one. And the result? Problems get solved way earlier, and the final product is just more elegant, more efficient, and a whole lot more powerful.
Every smart system needs a brain to make decisions. In the world of mechatronics, we call this the controller. And as we're about to see, choosing the right brain is one of the most important decisions you'll make in the entire design process.
This one question is right at the heart of the whole design process. And you might be wondering, why? Well, it's because your choice of controller is going to impact everything that comes after it: the cost, the size, and even how the machine gets programmed and maintained for years to come. It's a decision with some massive consequences.
And that brings us to our two main contenders. On one side, you have the PLC, the Programmable Logic Controller. Think of it as a rugged, standalone industrial computer. On the other side, you've got an embedded controller, which is basically a circuit board that's built directly into the machine it controls. So how do you choose? Let's break it down. The PLC is your industrial workhorse. It's more expensive, for sure, but it's modular, which makes it super easy to repair. You just swap out a part that fails. Now, the embedded controller is the lean alternative. It's way cheaper and a lot more compact. But, and this is a big but, if it breaks, you often have to replace the entire board. So you can see this isn't just a technical choice. It's a huge strategic business decision between getting to market quickly and the long-term cost. So we've got our brain. Now it's time to give our system the ability to actually interact with the physical world. And we do that through its muscles and its senses.
This diagram lays out the complete feedback loop perfectly. It all starts with the controller, our brain, which sends a command to an actuator, say a motor. That's the muscle that creates movement. Then a sensor acts as the system's eyes or ears, measuring what just happened and feeding that info right back to the controller. This constant loop of command, action, and feedback, well, that's the foundation of all modern automation.
And these senses, they can measure almost anything you can imagine. Position and speed sensors are like the eyes of a robot, telling it exactly where its arms are. Temperature and pressure sensors are absolutely vital for keeping industrial processes safe and efficient. And you've got everything from light sensors that can dim a room automatically to proximity sensors that can detect an object without ever even touching it. It's amazing stuff. Okay, we've got a brain, muscles, and senses. But how do we hook them all up? That's where the system's blueprint, its nervous system, comes into play. So this is the nervous system, all captured in a detailed drawing. Using standardized symbols, these industrial wiring diagrams are like a universal language for engineers. They show exactly how every single component is connected, how the power flows, and how signals get from one place to another through the entire system. And this blueprint is absolutely essential. I mean, not just for the initial build, but for the entire life of the machine. Can you imagine trying to fix a problem years down the road without this map? It'd be nearly impossible. This diagram is the single source of truth, for maintenance, for upgrades, and most importantly, for safety. The design is done, the parts are all assembled, the blueprint is complete. Now it's time for the moment of truth, bringing it all to life. This is the one question that probably keeps engineers up at night.
You can model and simulate everything perfectly on a computer, but the real world, it's messy. The process of bridging that gap from theory to reality is called commissioning.
Commissioning isn't as simple as just flipping a switch and hoping for the best. It's a very methodical process. First, you do all your pre-checks, making sure everything is installed right and all the wires are connected. Then comes the careful power-up and testing phase, where you validate every single function. Finally, once it's proven that it meets all the specs, you have the final handover to the customer.
Now, with all these complex technical steps, you'd probably think the biggest failures are something mechanical or electrical, right? But what if I told you the most common point of failure is something else entirely?
And there you have it. It's not a broken wire or a software bug that causes the most trouble. It's a breakdown in human communication. When the team on site can't coordinate, or when the vendors and the customers aren't on the same page, the whole process can just grind to a halt. It's a powerful reminder that even in super high-tech engineering, the human element is absolutely key.
So, after all that hard work, what's the end result? Well, the applications are just incredible. This whole integrated design approach lets us build machines like the Mars Rover, which is essentially a robot geologist working millions of miles away from home.
The impact is also deeply personal. Mechatronics is the science behind the most advanced prosthetics, which can actually sense nerve signals and translate them into fluid, lifelike motion. It restores a level of capability that we once thought was impossible.
And of course, it's shaping the future of how we make, well, everything. A 3D printer is a perfect mechatronics system. You've got a precise mechanical frame controlled by sophisticated electronics following software instructions to create a physical object from a digital file, one layer at a time. And this brings us to one last, pretty profound thought. This mechatronic approach is making our machines not just more efficient, but more autonomous, more capable of learning and adapting on their own. Which really begs the question, as our creations get smarter and more integrated into our world, where exactly do we draw the line between the tool and the creator?